how the number of bits in memories is increasing, right? So from 1 megabit all the way to 2 gigabit, etc. And if the algorithm takes linear time, then also you can see that the number of operations, the time it takes to run the linear algorithm also will be high, 128 seconds, I think. See, 128 seconds is a fairly big amount of time, 2 minutes. Whereas look at this, if it's n log n, then the 3000 or approximately 4000 seconds, which is quite a bit. And if it is n to the power 3 by 2, it takes so many hours. And if it is n square, this is a totally unrealistic number. So order n square algorithms are out. So your galloping test, etc., they are just theoretical. You can't run a galloping test for even 1 megabit, right? It will take 18 hours to run it. Right? So you can't do this. These are the March tests. So March 0 means write zeros. March 1 means write, here is the notation. Okay. M0 means it's a sub step. Okay. So in either direction, increasing or decreasing, write zeros. Then in increasing order, read zeros and then immediately write 1. Then in the decreasing order, read 1 and write 0. So he has given you the for loops also. So there are many marching algorithms. One of them is called MATS. It's a very simple one. It says initially in some order write zeros, whether increasing or decreasing. Then again it doesn't matter in which order, read zeros, and after reading a 0 write 1. So at the end of this second step you would have filled the memory with ones. Then again in some order read the ones that you wrote back. So as you can guess, this is a very simplistic algorithm. It doesn't possibly do a very good job of detecting faults. On the other hand, look at the other algorithms. They are more intelligent. So in either direction, fill the memory with zeros, but next you go in the increasing order and read zeros and write ones, and then decreasing order, read 1, write 0. So this is called MATS plus. Then MATS plus plus. So there are only two things we can do: write zeros, write ones, or read zeros, read ones. But the way we do it, okay, may be slightly different. Look at this March B. Initially you write zeros in some order, but then when you go to this second step, you have to go from 0 to n minus 1. There you read 0 and then write 1. Then again read back. Then write 0, read back, and then write 1. So by doing this, you may wonder why this is all being done. But it is to activate certain faults and detect them. Okay. So the more complex your algorithm is like this, the more time it will take. See, each one of these will take order n time, right? You are going through all the cells. So it will take n write operations, n read operations, n write operations, and then n read operations. So totally it will take 4n. This will take 5n. This will take 6n. This will take 7n, and so on. Okay. And this is the theorem that he was referring to. So what it says is that when you are going from low to high or high to low, if you do a read 0 and write 1 or read 1 and write 0, x and x bar are opposite values. If you are doing read 1 here, you should do write 0. If you are reading 0 here, write 1. If you have either of these, okay, then it detects all address decoder faults. So that is like a theorem. Okay, so both should be there. So you should read 0, then write 1, followed by read 1, write 0. So this is like a condition. Let us take an example of a cell with only 4 faults, 4 cells. So I have only 4 cells. So what are some possible faults? 0 stuck at 0, 0 stuck at 1, 1 stuck at 0, 1 stuck at 1, 2 stuck at 0, 2 stuck at 1, 3 stuck at 0, 3 stuck at 1. Then 0, when it goes from 0 to 1, maybe 1 will toggle. Like this we can keep on writing. There are a lot of such faults. There could be 2 is going from 0 to 1 and 3 will toggle. Then 3 is going from 1 to 0, 0 to 1 and 0 will toggle. There could be bridge faults, okay, address decoder faults. So unfortunately the list is very huge. Even for a simple 4 cell memory, the result will be completely, it's very large. So what is the algorithm we are doing? Let us say in some order, let us say increasing order, we write zeros. Then in the, let us say increasing order itself, we read zeros and then we write ones. Then in the decreasing order, we write read 1 and write 0. Then let us say in the increasing order we write. Suppose this is our algorithm. See, this will activate certain faults. If there is a stuck at 1 fault, it will get activated. Then when we read back, if we read, we were expecting a 0 here, and if we got a 1, obviously there is a stuck at fault or something like that. So all stuck at faults will be caught. All cells stuck at 0 faults or stuck at 1 faults can be caught here. You agree? We were expecting a 0, but if you find a 1, obviously some cell may be stuck at 1. And then we are writing a 1. In the process, we are toggling certain bits, isn't it? We are toggling 0 when we go from 0 to 1. That may activate some fault. Okay, for example, this fault. When we toggle cell 0 in this step, maybe 1 will change state to 1. So here when we go, it will not only detect stuck at faults, so all cells stuck at 0 faults will be caught. Plus any these coupling inversion faults, they'll also get caught. And the reason why we also have to have this guy is, I mean, why do we have to do in the decreasing order? Because we also have to worry about if 3 is toggling, it may cause 0 to change state, etc. So we have to do that also. So it's not enough to always go from 0 to, okay, this is also there. So we have to sort of alternate between 0 to n minus 1 and n minus 1 down to 0. So as you saw, MATS is one simple algorithm. MATS plus is next improved version, and then March A, March B, like that. There are so many algorithms, March C minus. So in the literature, they would present an algorithm, and they will, sort of argue what faults it catches. And as we go from MATS to March B, you can imagine that more and more faults will be caught. But it will also cost more, okay? Because more operations. Remember, the size of the RAM that we are testing is very high. It's in gigabytes. So even 7n or something like that, 7 multiplied by 1 gigabyte is still a big number. And even though read and write are still very fast, right, it will still add up, and your memory test may take time, right, a few minutes. You may have experienced this when in your PC there will be some diagnostics, right? When when you want to run diagnostics on your PC, you can do so, right? So that is about different kinds of memory tests that we do, marching algorithms. This is the most standard way of testing today, march tests. And what apparatus do you need to do that? Okay. Do you want to do this through an external tester? Okay, so here is my memory, and do you want to put an external tester to give you those addresses, etc., and then read all of them back? Then the external tester will compare. This is not advisable in more than one way, okay? Because the memory may be deeply buried somewhere, right? It is not, we rarely, there was a time when memories were standalone, okay, meaning we will manufacture only memory chips. Even now it is done, but today memories are embedded, okay. We have embedded memories. What does it mean? Today our technology is advanced and allows you to put many things in the same. So you can put CPU here, we can put SRAM memory. In fact, many memories may be there, many CPUs may be there. So this is what is called as a system on a chip. It is a complete system. You may have many CPUs, many memories, many peripherals, peripheral controllers, USB drive controller, and maybe some LCD controller, etc., etc. So there are many digital and memory blocks. So if I have an external tester, for it to be able to get access to this memory, etc., will be, not easy. We will have to do a lot of work here to allow the external tester to come and take control of the memory and test it, etc. And it will also be very slow. So today it is very common to use embedded BIST. We also put the BIST inside the so memory BIST. Memory is always tested using built-in self-test. So this March algorithm, there is a memory BIST controller. That memory BIST controller will generate the addresses according to March algorithm. So it knows that initially it has to go from 0 to n minus 1, then it will go from n minus 1 down to 0. That this memory BIST controller knows. Similarly, the memory BIST, it will also provide the data. Are we writing ones? Are we writing zeros? So data. Similarly, it will take the data back from the memory, whatever is coming in, and compare it with either 0 or 1. So address, data out, data in, right? And then maybe it will also tell whether to read or write. So initially maybe we are trying to write. So it will activate write, then it will start using a counter and put the addresses 0 to n minus 1. Then it is writing, so it will put a 0 maybe to. So when you do this write 0, so maybe a counter is used to generate the addresses from 0 to n minus 1. And then 0 is outputted as data out. Read write will be set to write. Then when we do the read 0, etc., so it will take the data coming in, compare it. Okay, so it has a comparator inside. And it will also log. So whenever there is a mistake, that means the expected value was 0 but we are reading 1. So there is a way to log all that information. So maybe it maintains a buffer of some kind where the information is logged, meaning at location row equal to 23 and column equals 45, I was expecting 1 but I got a 0. So this information is logged here. And there is space for a certain number of errors. See, if it has more than that many errors, maybe we don't want to use that memory. The idea is if the errors are tolerable in number, we can repair the memory. Repairing means if we find that in the memory a particular row there is some problem. Okay. So maybe we can decide that this entire row will not be used. We will have some extra rows and columns. Okay. So these are extra rows. And extra columns. So these errors are getting logged. There is an error here, there is an error here. So it is up to us how we decide to do. Maybe we can decide that this row will eliminate, this column will eliminate. That is up to you. You have to optimize. If you find a multiple errors on a particular row, maybe it is good idea to eliminate the entire row and bring another row in its place. Okay. So when the memory is trying to address this row, let us say this row is 23, it will be redirected to another one. Let us say it is 141. Similarly, if it is trying to address a particular column, we may have decided that this entire column has a number of faults, so we are going to eliminate it. So another column will be brought in its place. So extra rows and columns are already built, okay, and an optimization is done in order to sort of eliminate the bad rows and columns and use the extra rows and columns to fill in their place. That is called as memory repair. Repair meaning it's not that we are going to repair anything, it's just that we have some built-in fault tolerance, extra rows and columns, and we will use those extra rows and columns to sort of help us overcome the barrier. Okay. So that is what is called as, some people will refer to it as built-in self-repair. So the memory will repair itself. So here is one possible organization. We have a memory. It has an address. It has some data coming in. There is some data that is going out. And it has a control, read, write control, etc. So normally there may be a CPU or something like that which generates the address. Normally there is a CPU which writes to this memory. Normally there is a CPU which reads the memory. And normally a CPU will generate the read write. But in the memory BIST mode, the memory controller, BIST controller, will produce an address, and the CPU address and this address will be multiplexed. Similarly, the BIST controller may provide some data that is based on the March algorithm, and the CPU data and the the data provided by the memory BIST controller, they are going to be multiplexed. This data will go to both CPU and the memory BIST controller. This will come from CPU. Similarly, in the BIST mode, the BIST controller may this data is coming from CPU, this data is coming from BIST controller. This data is going both to CPU and the BIST controller. And read write control also may come from both so CPU read write and the BIST controller. And as I mentioned, the BIST controller can log the errors. So you can see that in order to do this, and there is a comparator, I suppose. So it will require a comparator. So to practice memory based, you will need a BIST controller. You will need the muxes. You will need extra wires. Right? These wires were not there originally, right? So all this will add to extra area. And power. And they will impact the performance. Because see, the address bus may be 32 bits. Okay. So we have 32 wires that have to go from the BIST controller to that multiplexer. So a lot of wiring. Right? So it is possible that somebody may say it's a lot of extra overhead. So they may want to reuse a CPU itself can do the job of a BIST controller. So in that case it's called CPU BIST. This is also allowed. Only thing is the CPU itself could be bad, right? It's a possibility. So we have to rely on, when we are testing the memory, we assume that the CPU is okay. So CPU BIST means we don't want to have a BIST controller, etc., etc. CPU itself will apply the March algorithm. And to make to make the matters worse, it's not that there is one memory, right? There is a lot of memories. So in a big chip, there may be hundreds of these memories with various sizes. So there could be a 1K by 8, there could be a 16K by 8, there is a 2K by 16. Like this, so many memories may be there for different purposes. Maybe some of them are used for storing images. Some may be storing some data from ADC. And so on and so on. So testing all of them can be a very big challenge. Are you going to provide separate memory controllers for each of them? That will make the area etc. too high. Okay. Can we have separate MBIST controllers? MBIST means memory BIST. this is too difficult. So it is common nowadays to share the same memory BIST controller across all the memories, and that BIST controller will can be programmed to test the memories in a certain order, what algorithm to use, should you use march B, should you use march A minus AB, march C minus, okay. So this is what is called as programmable BIST, PBIST. So it can be programmed by the user or the test DFT engineer to apply these algorithms. Different memories may require different algorithms, right? A larger memory may require a different algorithm, and a smaller memory may read a different algorithm. So that programming is done through what is called as PBIST.